Today we are seeing a couple of calculus related operations on the parametric curves. So basically we have a parametric curve and that represents maybe a path of a particle, and then we can actually compute tangents and the slope of the tangent line at different points. We can find horizontal and vertical tangents, find the area enclosed by the curve, length of the arc of the curve. So basically we are going to see how to compute those things based on the parametric equations. So a parametric curve is given by the parametric equations. So we have an equation for x and another one for y. So they are all both function of a third parameter, t. This could represent time or an angle or some other quantity. So basically what we want to do now, once we have our parametric curve, we want to maybe find the slope of a tangent at some point, and then maybe even the equation of the tangent line, find where the curve has vertical or horizontal tangents. So that's something easy to compute, and also length of the curve and eventually the area under the curve. And we will see that we can get speed of a particle almost for free based on the computations that we are going to do on the equations for the x and y, these parametric equations. So there are a couple of formulas only to remember here. In order to compute the tangents and the slope, basically what we do is we need to compute the slope of the tangent line, and that's the first derivative, dy dx. So how do we compute the derivative, dy dx, when x and y are functions of t, and eventually y is a function of x also. So basically this is a formula. So we have variation of y in time, so dy dt, and variation of x, dx dt. So it's quite simple. So we just have the ratio of two derivatives, dy dt and dx dt. Obviously in this case we need to assure that dx dt is not zero, so we don't have division by zero. But we will see what happens in this situation also. So this expression gives us the slope of the tangent line. So that's quite straightforward. So we have expressions here for x and y. We simply differentiate them with respect to t and then compute the ratio. So what happens if we have dy dt or dx dt equal to 0? So again, this is a slope of the tangent line. So if dy dt is 0 but dx dt is not, so basically we have 0 divided by some number different from 0, well, the slope will be 0, which means we have horizontal tangent. So for that value of t, we can find the point on the curve just by plugging the value of t in x of t and y of t. So that will give us coordinates of the point where the curve has horizontal tangent. Also, if dx dt is 0 but dy dt is not, so we have some number different from 0 divided by 0, so basically this will explode, so we have vertical tangent in that point for that value of time. So we plug the value t into the expression for x and y, and we get the coordinates of the point where we have vertical tangent. So we will see some examples. So these are straightforward computations. So this is the same summary written a little bit differently. So we have parametric equations x and y, and when the derivative of y is 0 but derivative of x is not, so basically the numerator is 0 and the denominator is not, we have horizontal tangent. If we have the opposite situation where the denominator is 0 and numerator is not, then we have vertical tangent. So now what happens if both of them are 0 at the same time. So basically we have indeterminate form 0 over 0, right? So this is a classical definition of the slope, right? So of the derivative. So what we need to do in this situation when we have 0 over 0, we will need to compute the limit, and in that situation when we need to compute the limit of indeterminate form 0 over 0, we will use L'Hopital's rule. So even in this situation things are not too complicated. We can interpret these derivatives as horizontal and vertical velocities. If we imagine that our curve is actually a path on which a particle is moving or some vehicle is moving, so variation in x direction, so dx dt is considered horizontal velocity, and then dy dt is vertical velocity. Okay, so that's just an interpretation, and then such what we have is the velocity vector that is actually the derivative of x and the derivative of y. So we need to find the speed. Speed is just the module of the vector, so basically the first component squared plus the second component squared and the radical. So this is quite easy in this situation to compute the speed of a moving object. Just by having the first derivatives we can compute it very quickly. And velocity, the speed will be 0, so the object is not moving when both of these derivatives are 0, obviously. So those are like straightforward computations just from the parametric equations and their derivatives, straightforward. Now, on top of having the slope of the tangent line, we can also find the concavity of the parametric curve. So we can find regions where the curve is concave down or concave up. For that we need to compute the second derivative and figure out the sign. Intervals where the sign is positive, we will have concavity up, and intervals where the sign is negative, we have curve concave down. So basically we need to compute the second derivative. So how do we do that? Well, we take the formula for the first derivative, and in that formula we replaced y by dy dx. So simply replacing y by dy dx, so you get the second derivative, right? Just replace in this formula y by dy dx. So here we have y replaced by dy dx. So it's a just graphical replacement. So this gives us the formula for the second derivative, and depending on the sign and the regions where the sign is positive or negative, we will have our concavity. Here is one example just to see how things work. So we have a parametric curve described by these two equations, and the first task is to show that the curve actually has two tangents at point 30, and then we need to find their equations. After that we will try to find points where the curve has horizontal and vertical tangents, and then obviously we can compute the second derivative and find where the curve is concave up and concave down. So the first task was to find the value of t for which x is 3 and y is 0, because we need to locate the point 30, and for which values of t the curve passes by the point 30. So we need to find all the values of t for which x is equal to 3 and all the values of t for which y is equal to 0, because in this case the curve will pass by the point 30 several times. So we need to find what times it passed through that point. So basically we need to solve the equation 3 equal t squared. So we get the first two options for t, and then we need to plug these values into the equation for y to see if y is equal 0 at that time, because the point is 3, 0. So x needs to be 3 and y needs to be 0. And indeed it works. Actually y is equal to 0 at at t0, and also radical 3 and minus radical 3. But our point that we need is 0.30, so we are only focusing on the values of the parameter t at radical 3 and negative radical 3. So we are passing by the 0.30 only at the time radical 3 and negative radical 3. And the point in question is 0.30 on the curve. So that was the first thing, because to find the slope, we need to plug the value of time into the derivatives. So now the values of time are 3 and negative 3. Because at those two different points in time, the curve is crossing the location 3, 0. So let's compute the derivatives. So dy dt and dx dt, and then we compute the ratio. So we get this, so the derivative of x here is 2t, and here is 3t squared minus 3. So now we need to plug the value of time radical 3 and then also minus radical t to get two different slopes. So once the computation is done, the slope is also radical 3 and negative radical 3. So it means indeed our curve has two tangents at the location 3, 0. One tangent line has the slope radical 3, and the other one has the slope negative radical 3. And this is the equation of the tangent line. So it is y minus 0 equal to the slope times x minus 3. Okay, so we quickly saw that our curve at the location 3, 0 has two tangent lines. Now the next task is to see at which location and which time we have horizontal tangent and then later on vertical tangent. So to have a horizontal tangent, dy dt, so the numerator needs to be 0, but denominator should not. So then we don't have any issues, we have dy dx equals 0. So at which point in time dy dt is 0? So we try to find the time for which t squared is equal to 1, so those are plus and minus 1. And our derivative for x is 2t, so it's only 0 at 0, so basically we don't have problems at plus or minus 1. Great, so that means at time plus 1 and minus 1, the slope is 0, so we have horizontal tangent. Now we take value of time 1 and we plug it into the equation for x and y, so it will be 1 and then minus 2. And then the next thing, we put the value of time negative 1 in the equation of x and y, so negative 1 squared is 1, and here if we put negative 1 we get 2. So those are the 2 points on the curve where the tangent is horizontal. Okay. Can we find points where the tangent is vertical? That means that dx dt should be 0, but dy dt should not. So the only point where the x prime is 0 is at t0. So if we put t0, we have 0.00. And obviously dy dt is not 0 at 0, because when you put 0 here you get minus 3. So we have vertical tangent for time 0, and the location, the point is the 0.00, so the origin. Now for the concavity we need to compute the second derivative, which means we need to use the formula where we take our first derivative, differentiate with respect to time, and then divide by dx dt. dx dt was also computed already. So once the computation is done, we have this expression here. So now we need to see the sign of the second derivative. So the numerator will always be positive, so that's not an issue. So the sign depends on the denominator. So for t greater than 0, the expression is positive, so its curve is concave up. And for t negative, the expression is also negative. That means the curve is concave down. So after sketching, we get the shape of the curve. So we see that at the point 3, 0, indeed we have crossing. Curve is crossing itself. So we have two tangent lines. When we travel on the curve from this direction, we have one tangent line, and then as we are coming back, looping back, we are on the other branch of the curve, so we have a different tangent line. So the same point, this is point of intersection of the curve. It has two different tangents depending on our moment in time, so basically from which direction we are coming. So if I'm traveling this way, our tangent will be this one, and then when we looping back a little bit later, we have a different tangent. And we see at the point 0, 0, indeed we have a vertical tangent, and at the points 1, 2 and 1, negative 2, we have horizontal tangent. So obviously the questions that are given, all these quantities should be fairly easily computable, otherwise it can take a long time. So in this situation, we have a different curve, and we would like to find the slope and the slope of the tangent line at t0. So that will be easy. We just compute the derivatives and then do the ratio and plug t equals 0. So that will be straightforward. And the other task is to compute the slope at the point 0, minus 3. So our expressions with the derivatives will have t in them. So we need to plug some value of t, but we need to first find the t for which the curve passes by the point 0, negative 3. So we need to find all the values of t for which x is 0 and y is negative 3. So that will be a task for us to find the values of t such that x is 0 and y is negative 3. And then at those values of t, we will evaluate the derivative. So that will be more complex. The first part is just straight computation and plugging the numbers. So that will be straightforward. So the derivatives, we compute directly the derivatives of x and y. And then the slope, the formula is simple, it's dy dt over dx dt. And we evaluate that at time 0. So that just plug the numbers in, and we got the slope 1. So that was straight computation. Nothing particular there. Now, for the second question, we need to find the slope at the point 0, negative 3. So the first task is to find the values of time when the curve passes by the point 0, negative 3. So we need to find t such that x is 0 and at the same moment y is negative 3. So we need to solve that, and the solution will be 3 pi over 2 after some work. So at that moment in time, the curve is passing by the point 0, negative 3. So now we use that point in time to evaluate the derivatives and to compute the slope. Unfortunately, at this moment in time, both derivatives are 0, so we have 0 over 0. So we have a problem with computation of the slope. So now what do we do? Well, in the case we have 0 over 0, we will use the limit and L'Hopital's rule. So basically, we have our slope here, dy dx, and we need to compute the limit when we are going to 3 pi over 2. So it will be indeterminate form 0 over 0, so we use L'Hopital's rule. You see the numerator was differentiated and denominator also, so we use L'Hopital's rule here. And then when we try to evaluate, we see that the numerator is going to 6 and the denominator is going towards 0, so basically this ratio is exploding, so which means we have an issue there. So we probably have some type of vertical tangent there, even if we don't see it right now. So the slope as it is doesn't exist because the limit doesn't exist. And the reason is, from one side the expression goes to plus infinity, and when we come from the other side it goes to plus infinity. So plus infinity minus infinity as a slope is a problem. So indeed, from the graph we see that the point 0, -3, if we are on this branch, the slope will be negative and then increasing towards plus infinity, and if we are on this branch, the slope is positive and increasing to plus infinity. So that's why we had a problem computing the slope here, because we have an issue with the corner. So in this situation here, what happened is we had a problem because we had indeterminate for 0 over 0, and then we used limit and L'Hopital, and then we found out that actually the slope doesn't exist, and now we see why based on the shape of the curve. Obviously, when we have all the derivatives, we can compute easily the speed of the particle. So when we have derivatives, we remember that the speed is derivative of x squared plus derivative of y squared, and then we take square root of everything. So basically that's simple computation. So the derivatives, we evaluate them at 0, because the question was to find at time 0, find the horizontal vertical components of the velocity and find the speed. So that's straightforward. So horizontal component of velocity, vertical component of velocity, evaluate at t0, we get the speed at the point y0, x0, y0, so at the time t0. So the point is 2, 1. In that point, the speed of the moving particle is radical 8. So that's straightforward computation. Okay, so now the question was also to find all the values of time and also the locations where the speed is 0. So the formula for the speed is here, so we need to make sure that this expression is equal to 0. What are the values of time? So that's a little bit more complicated because we have these trigonometric expressions here. So you see the computation can take a while to process in order to find an expression for the speed. So it's this radical here. So now we need to find all the values of t for which this radical here is 0. So that's again a little bit longer. So basically we need to find all t such that 1 minus sine 3t is equal to 0. So sine 3t needs to be equal to 1. And then we know that sine of an angle is 0 when the angle is pi over 2, 3 pi over 2, etc. So basically we need from there we need to compute the values of the angle. So this involves a little bit more work, and then once we find these values of time, we need to plug them into the equation to find the locations x and y. So this takes a little bit more time, obviously, to compute. And on the graph we realize that those points are these 3 corners, and then they keep repeating because the movement of the particle moves along the path non-stop, because here we didn't have any restrictions on the parameter t. So the procedure is quite simple and logical. Now the computations might be more difficult because you see you need to make sure you don't make any errors expanding all these squares and then simplifying the expressions. So this work here is obviously tedious, but the principle is simple. So then hopefully the questions that we need to solve will not require this much work, because obviously it takes some time. So a different curve, so we have two parametric equations, and the question is just find the points, so the locations where you have horizontal, vertical, tangent lines. So again, we compute the derivatives, we compute the dy dx, and then we start to figuring out when we have horizontal tangent, which means dy dt is 0 but dx dt is not, and vertical tangent when dx dt is 0 but dy dt is not. So the principle is simple. Now implementing this might be more challenging depending on the algebra involved. So the curve in question looks like this, is generated by a graphing computer, right, application. So from here we need to find essentially the points with horizontal tangent. So these 2 points, we need to find their coordinates. Point with vertical tangent, we need to find the coordinates. In some questions you might be asked if it's computable quite easily, the point of intersection. So that means you need to find 2 different values of time, or parameter t, for which x and y are the same. So x is the same at t1 and t2, and y is the same at t1 and t2. So basically you need to find 2 moments when you pass by the same point. Okay, so in itself it's not a complicated process, but computation might be heavy because the particle is traveling this way. So at time t1 it passes by the point here, and then it goes all the way around, and then at the time t2, some different time, it passes by the same point. So that's how we recognize that we have a loop, and finding, so the principle is simple, finding the time and the location where the loop happens, that's another story. It's much more involved. So the simple computations involve these derivatives and horizontal tangents and vertical tangents. So the principle is simple. Now finding all the values of t, that's maybe more involved in the process, but you need to understand the principle how to do these things. So basically after that the computation might be straightforward or a little bit more demanding depending on the question. So for the vertical tangent, dx dt needs to be 0, but dy dt should not. So basically again it's a little bit of algebra. Another thing that we can do on top of computing the slope of the tangent line and the equation of the tangent line at a certain point, we can also find the area maybe enclosed by the curve if we have a loop, or between the curve and x-axis, or the curve and y-axis depending on the question. So here what matters is when you compute the area, we need to make sure that we traverse the curve exactly once in a period of time, and then the formula for the area will be simply y dx. So y, we take the expression of y, and dx is the derivative of x with respect to time, and then we integrate with respect to time, so that's why we need the time interval. So it's quite simple as principle. Now again, the computation the complexity will depend on the complexity of the expression that we have here. But the area in itself, the formula is straightforward. If you are given the function and interval for x, you will need to find the interval for the parameter t. So at which time do you have x equal to a, and at which time you have x equal to b. So that will be the work in itself. So that's how we find the limits of integration on with respect to the variable t. So we need to find the time that corresponds to the value x equal a, because here the bounds are a and b in x. So we need to find equivalent to a, but in terms of the parameter t. So that's some work that needs to be done in order to find the new limits of integration. So here, if we have an illustration, one arc of the cycloid, so what's the area under the arc of the cycloid? And the formula is given there. So one arc happens when the circle rolls from 0 to 2 pi. So the angle varies between 0 and 2 pi. And then the formula is simple. For the area is y times dx. So we plug the expression for y, compute the derivative of x, and plug it there. So suddenly it's a little bit more complicated as expression. So you see we need to expand the square, so the computation might start being a little bit more involved. There are two pieces that are easy to integrate, and then we have cosine square, and then we will use half angle formula for the cosine. That will simplify our life in computation of the derivative of the integral. So basically this becomes now the fight to integrate the expression, but the principle in itself is quite straightforward. So expression for y and then dx, and our angle varies from 0 to 2 pi, so that's straightforward, it's finished. So as long as we know the bounds on the parameter, we are good to go. So in this case it was straightforward. Again, computation can be more or less involved depending on the expressions that we have. Another part another question that we can answer actually is the arc length of the curve. And again, we need to make sure that we traverse the curve only once, because we don't want to compute double the length. So that's why it is important to delimit correctly the interval for our parameter. But the computation of the arc length is quite simple. So it's the integral of the radical of the square. So you have square of the first derivative plus square of the second derivative of x and derivative of y. So you square them, add. So basically it's a simple formula. Now again, depending on the expressions, it will be more or less complicated to actually compute the exact value. So when we know the computation can be done, let's say easily, we can ask for the exact value of the arc length. If we know that actually the integral here will be extremely complicated, we can just say set up the integral, or find the expression of the integral that describes the arc length. So basically you just set up the things and you leave it as is, because the computation of the integral might be very challenging. And again, what matters here is that we make sure that the curve is traversed only once. So we need to be aware of that, and because the bounds here, the integration, the limits of integration on our variable, on the parameter t, they need to be such that we make sure that we traverse the curve only once. So in the case, for example, when we have a circle and we want to find the perimeter of the circle, so basically the arc length of the curve that is circle, and if we describe circle by sine t and cosine t, then our parameter travels from 0 up to 2 pi and describes the circle only once. So we traverse the circle only once with this formula. However, if we use a different formula, sine 2t and cosine 2t, now if we leave our parameter run from 0 up to 2 pi, we will traverse the circle twice. So you have frequency here. So you're running around the circle twice. So that would be a problem, because now we have the length that represents actually twice the arc length. So it's twice the parameter. So we need to be careful. If we use this expression with sine 2t and cosine 2t to describe the circle, we need to make sure that with this expression we traverse the curve only once. And for that to happen, our parameter needs to run from 0 to pi. So 0 pi. Because we use the description of the circle sine 2t cosine 2t. So that's the idea here when we say curve needs to be traversed only once. Pay attention to the formulas and make sure that curve is traversed only once. So the bounds on the parameter here need to be such that they ensure that we traverse the curve only once. In most cases that is by default, but it's just important to realize that you, for instance, for the circle you can have several descriptions, and depending on the descriptions, but you need to make sure that your parameter runs in a correct interval. So one of the cute questions is again involving cycloid, and the question is find the length. So we found the area, we can find the area, we can find the length of the one arc of the cycloid. So again, the one arc of cycloid is accomplished when the angle goes from 0 to 2 pi. So the formula for the length was quite straightforward. Now the computation, that's another story. So the formula here, we need derivative of x and derivative of y, we square them, take the radical, and we integrate between 0 and 2 pi. So that's the expression. We set up the integral, let's say, quite easily. Now how do we get 8r as a result? Well, that's another story. So basically we plug the expression, so the derivatives are here, we square them, plug them into the expression, and now we need to simplify things as much as we can. So we come up, like with simple algebra, we come up to here, and then we are a little bit stuck now, because now we have in the radical 2 and factor of 1 minus cosine theta, so this becomes a little bit challenging. But then we realize, oh, this looks like a part of an expression for half angle of somebody. So is it sine or cosine? But with the minus it's going to be sine. So that gives us an idea. So let's see what we can do with that idea. So our issue is to integrate this expression here. So basically the part 1 minus cosine theta reminded us of half angle formulas. So sine square is expressed this way, and then we go, okay, so let's work on this expression to replace 1 minus cosine theta by something that is squared. So when we take the radical, things simplify a little bit. So again, if you don't have this idea, well, you're stuck, you cannot progress. So basically now when we have this half angle formula, we can replace things back. So 2 times sine square, obviously we have theta, here we have 2x, so we just replace one by the other, it's fine. And then we have a much simpler expression with sine square inside the radical. Now for the interval we are interested in, sine will be positive, so we have absolute value that is actually equal to the sine. So this simplifies things a little bit, but the key idea was this half angle formula. Without it we have a serious problem. So now when we have a simplified expression, now we just need to integrate sine. But again, these computations can be more or less delicate and complicated depending on the expression that we have. The surface area, I'm just showing it here, but it is not necessarily included. but it's good for you just to see. It's actually, the process is the same as what we did previously for the surface area. So we have integral, so we have our parameter t between a and b of 2 pi times radius times arc length. So we need to figure out what is the radius, what is the arc length. So if we are spinning around x-axis, the radius will be y, and if we are spinning around y-axis, the radius will be x. And then we have arc length expression as is. So obviously in our case, arc length expression is this radical here. And again, the formula is simple. Implementation and computation, that's another story depending on the expressions that we get. But what matters is when you rotate around x, you see you have 2 pi y. The radius is y, and then this is arc length here. And if we are rotating around y-axis, we have 2 pi x as radius, and then the arc length, the radical. So those are straightforward formulas. Computation might be more involved. For instance, if we want to compute surface area of a sphere, how do we get the sphere? So we take half circle, so semicircle here, and then we spin it around the x-axis. We will get the surface area of a sphere. Okay, so that's fine. The sphere will be there just by spinning this semicircle around the x-axis. So we need to find the formula for to parameterize this curve. So here it is. So x is equal to cosine t and y is sine t, and we go from 0 to 2 pi. So we start here and we complete at t equal pi. We are here. So this is an important part of the process to know what is the range for the parameter t. So now we have all the pieces. Since we are spinning around x-axis, we have 2 pi y, and the bounds on our parameters are 0 and pi, so 0 and pi, and we have this expression that we need to compute, so the derivatives, and then we square them and then we add them. So 2 pi y is r sine, right? So we will replace it here. So all the expressions are replaced, so we will end up only with one gigantic expression in terms of t. So we are fortunate these things simplify a little bit. So now we integrate only the sine between 0 and pi. So basically this was a straightforward integration in this case. So here we have a semicircle and we were rotating it around x-axis. Now you can generate a sphere also if you take a semicircle that is a little bit different. So if I, instead of having x equal cosine, I have x equals sine t and y is equal cosine. So basically what happens in this case, we start from this point 0, 1 and we end up here. So we have a different semicircle. So to get the sphere, we need to rotate this semicircle around y-axis. So, and in that case, the formula is 2 pi x and then the length. So pretty much we will get the exact same result. Everything is the same, but we just need to be aware of the situation because our parametrization was different. So we got a different semicircle, and in this case we had to rotate it around y-axis. So if we rotate about y-axis, well, in the formula it's 2 pi x. The radius is x here, right? So that was the idea. And again, this is just to illustrate things. We are not going to focus on these questions because the computation can be quite challenging. Now the good news for you, you have a couple of exercises that are quite easy and straightforward because they were adjusted. So if somebody is asking for the slope of the tangent line, the computation is quite straightforward. If they are asking when is the tangent horizontal or vertical, again the expressions are adapted. If the question is about concavity up or down, again computations will be simpler. So basically all these questions that you have here are quite straightforward using the formulas, no heavy integration involved. And as you remember, you have the solution manual also, and all of these questions, so even and odd, are solved in detail there in case you want to verify your work. Now, an example, which is maybe an artificial example, because in no example of our own we will have all of these questions, and you will see why, because some pieces are very heavy in computation. So let's say we have a parametric curve described by these two parametric equations, and then now we want to find everything we have talking about. This is again extremely rare that one curve we will ask everything on one curve, because again computation might be challenging, especially for the integrals later on, so it's not so obvious. But let's try to do what we can on this particular one just to have some fun. So we would like to have time and points when we intersect x-axis and y-axis, just to see how it looks like. And then the time that corresponds to the point 15,2, so something that should be easy to find maybe. And then the slope and the equation of the tangent line at point 15,2, so that's why we had to find t first, because these derivatives involve t, so basically we need to have t corresponding to the point 15,2. And then we want to find time and points where the tangent is horizontal or vertical. Then what are the intervals for concavity up and down? So you see there's a lot of work here. And in this particular case, the curve is creating a loop, so it is intersecting itself. So we would like to find, if possible, coordinates of the point where the intersection happens, and the time, two moments in time where this intersection happens. So that's a challenging request. And then we would like to maybe have an arc length of the loop, because we have a loop here. So how long is the loop? What's the length of the loop? So in this case we can set up the integral. The computation is of the exact value is challenging. And then the area enclosed inside the loop, again we can give an expression for the, so we set up the integral for the area, but we don't compute it. And again, this is very exhaustive analysis here, and it will take some time to compute. So that's why in our questions we have maybe only one or two of these pieces depending on the curve, because the computation obviously needs to be a little bit more affordable than what we have right now here. So just to see how things work. So if I have this parametric curve described by these two parametric equations, and I want to find time and points where we meet x-axis and y-axis. So that shouldn't be that difficult given these expressions here. So we intersect x-axis when y is equal to 0, right? We cross x-axis when y is equal to 0. So let's find the points where in time, so moments in time where y is equal to 0. So we need to have this expression equals 0. In this case, we plug some numbers quickly, and we find that at t1 and t2, actually we have y equals 0. So the corresponding point for t equal 1, so we plug t equal 1 in the expression for x and the expression for y, obviously, and we get the point 3, 0. And at the moment t equal 2, so we plug 2 in the expression for x and 2 for the expression for y, we get the point 8, 0. So at these two locations our curve is crossing x-axis. Okay, so when is the curve crossing y-axis? Well, that happens when x is 0. So basically, what are the values of t for which x is 0? Well, again, because of this nice expression here, we can find these values quite easily. So at the time t0 and time t minus 2, x is 0, so what are the values of y? So at 0, if we plug 0 here, we have 1 minus 0. So at t0, the point is 0, 1. And at time t2, so we plug 2 here, so we have 4 minus 4, right? Oh, it is t minus 2. So at t minus 2, 2 to power minus 2 is 1 over 4. And this will be minus 2 times minus 2, that will be 4. So 4 plus 1 over 4 is 17 over 4. So there is an error here, it needs to be negative 2. So those are the locations. So these 2 points are locations where we cross y-axis. So that's nice. That was quite straightforward in this case. Now, what is the slope? First, what is the time corresponding to the point 15,2? So which means for which value of t x is equal 15, and at the same time y is equal to 2. So we need to find those two values of t. So basically x needs to be equal to 15. So 15 is equal to this. So basically we have this expression, and the points in time are 3 and minus 5. So we need to check for which one of these y is equal to 2, because x in both cases for 3 and 5 is equal to 15. That's all right. But is y equal to 2? So if we plug t equal 3, we will find the point 15,2. That's the point we were looking for. And what happens at the time t minus 5? Well, when we plug here, we have a point that is different from 15,2. So in our question, we wanted time that corresponds to the point 15,2. Well, that time is t equal 3. Okay, so for t equal 3, we are at the point 15,2. So that's cool. It was not too complicated. Now, what is the slope at the point 15,2, and what is the equation of the tangent line? Well, now when we know the time, that t is 3, at time t equal 3, we are at the point 15,2. Well, all we need to do is compute the derivatives and plug t equal 3 in the derivatives. Simple. So the derivatives, that's straightforward computations. Just be careful here, derivative of 2 to power t ln 2. So be careful. So we have the expression for the derivatives. We plug time t equal 3 in these expressions. So t equal 3, so we plug it in and we get a value for a slope. I kept it as is, didn't try to get an approximation in decimals, but you could, it's fine. So basically we have a slope here at the point 15,2. Okay, so what is the tangent line? Well, the formula of the tangent line, we remember, is here. So we have a slope times x minus component x of the point, which is 15, plus component y of the point, which is 2. So that's our tangent line. So again, in this case, computation was straightforward. Once we got the value of t corresponding to the point 15,2, it was just question of plugging the numbers. So now things might be a little bit more challenging. We need to find time and the points when we have horizontal tangent and vertical tangent. And again, we use the equation of the slope, and we know that the horizontal tangent happens when dy dt is 0 but dx dt is not. So we need to figure out when dy dt is 0. So we have the expression dy dt here. It needs to be equal to 0, so we need to solve. And at for the same value of t, dx dt shouldn't be 0. Well, we see that dx dt is 0 only when t is -1. So as long as we are not at -1, we are fine. So now we need to solve this equation here to find t. So processes involving some logs. So you see the expression is ugly. Obviously we can evaluate it using calculator to get an approximate value, but I just kept it as is. So you see now computation starts being a little bit more involved. It's not scary, but still. So for this value of t, the dy dt is 0, so we have horizontal tangent. Okay, so what is the point? What is the location on the curve? Well, we need to take this value of t and plug it inside the expressions for x and y. So that will give us location. So this is an approximate value for t. So we take this and plug it into expression for x and y, and we get coordinates of the point where the tangent line is horizontal. So again, the process is, the logic of it is simple. Implementation, well, in this case it was not too bad, but obviously it could become more complicated depending on the expressions. So now the vertical tangent, we need to find the t where we have vertical tangent, and then find the corresponding location, the coordinates x and y for that value of t. So again, from the equation of the slope, the vertical tangent happens when dx is 0, but dy is not. So let's first find where dx is 0. Well, dx is 0 only at -1, and at -1 dy is not equal to 0, so we are good to go. So we have vertical tangent for t equal -1. What is the location? What are the coordinates of the point? Well, we take -1, we plug it in the expression for x, and then in the expression for y, and we get the coordinates. So those are the coordinates, -1 and 2.5. So at that point we have vertical tangent. So you see the t corresponding to the point is -1, and this is the location on the curve that has vertical tangent. We can push things further and try to find the intervals of concavity, concave up, concave down, and again we need to use the formula. So we remember that the first derivative, so dy dx is here. We need the second derivative, but the second derivative involves some more computation, so here's the formula, we remember. So in the first derivative we replaced y by dy dx, so that's what happened. So now you see we need to differentiate dy dx with respect to t. Once we've finished, we divide by dx dt. So dx dt is already computed, it's fine. Dy dt, we computed it already. So now we have dy dx to differentiate with respect to variable t. So this will be quotient rule here. So again, now things become a little bit more involved, so the algebra becomes messy. So that's why in our case normally we have questions that are tailored for the curve that we have. So if we are asked to find concavity up or down, well, normally these computations should be simpler, not messy as this one. So, but this was just an illustration to see everything combined in one question, even though it will be very messy and maybe impossible to solve for everything. So the first part is this. Now we need to divide it by dx. So we divide it by 2t plus 2. So again, it will be messy. So we get this expression at the end. So that's beautiful. We have second derivative after some heavy work. Now we need to figure out the signs. For which values of t this expression is positive and for which value of t is negative. So now if we plot, so now obviously we cannot figure out the sign of the numerator easily. So I just tried to plot the curve and it was always positive, so that was a good news. Obviously you cannot do that in the exam setting, but the curves will be, the expressions will be adjusted obviously, but this is just an illustration to try to do everything with one single curve, and you see why things are separated in your case in pieces, because things get messy very quickly. Now the denominator is positive for t greater than -1 and negative for t smaller than -1. So since the numerator is always positive, the sign of the second derivative is determined by the denominator. So we have essentially the intervals of concavity thanks to technology. Now the next thing is find the point of self-intersection. So basically the particle is traveling along the curve that is described here, and we want to find two. So basically there is a loop, there is intersection of curve by itself, but that happens at two different points in time. See, we would like to find those two different points in time where the curve is crossing itself. So we have a same location but two different points in time. So this, again, the computation is quite challenging in this case because there's a lot of algebra behind this. So we need two different points in time, so moments in time, where x is the same and y is the same. So xt1 and xt2 is the same, and yt1 and yt2 is also the same. So we have the same point at two different moments in time. So the principle is okay, it's not that complicated. Now finding those values of t1 and t2, that's another story. We just know that they need to be different. So if we say t1 is the first that happens and then the t2 is the next one, so basically t1 is smaller than t2, which means that t2 is t1 plus some value in the delta. We don't know what is a, but we know it's going to be positive because t2 is bigger. So we have one moment in time, and then sometime later we pass by the same location again. So that's why we have t1 smaller than t2. Okay, so if I just re-express t2 as t1 plus some number, positive, that will be helpful here. Algebra is extremely messy. I'm not presenting it. It's quite something. And again, that's why we don't ask these questions blindly. We make sure that things are workable, but here I just tried to do everything, and it was a lot of suffering to find t1 and t2 actually. So the principle is the same at two different moments in time. X needs to be the same and y needs to be the same. So I just plug t1 and t2 into these expressions. So x with t1 needs to be equal to the x with t2, and then y, expression here, at t1 needs to be equal to y at t2. So the principle is simple. Finding the t1 and t2, that was something. So from this first equation, after some work, we get a relationship between t1 and t2. So t1 plus t2 is equal to -2. Okay, so that gives us something. It locates a little bit things. And then from the expression yt1 equal yt2, after some work and using this condition here, we get another condition. So we need to find now t1 using this expression. So we need to solve for t1, which is not obvious at all. And we figured out also that this needs to be negative. So the work behind this takes quite some time. So I skipped it. I'm just presenting the end result. So finding now t that solves this is again a challenge. So in this case, after some work and using some technology and graphing, we found two solutions. One that is not admissible, which is t equal -1, because in that case then t2 is also -1. So both of them are equal to -1, but that's not admissible because we have two different points in time, two different moments, because the particle is traveling along the curve and crosses a point at some moment, and then some time later it comes back. So t1 and t2 must be different, obviously. So the easy solution was not correct because it was not respecting the conditions, t1 smaller than t2. And then the other one was actually correct. So we have t1 and t2 thanks to the relations, the condition that we found earlier. So now we have t1 and t2, we are all happy, and we get approximate values for the location, so the coordinates of the point, coordinate x, coordinate y. So obviously this is not exact value, it is approximate to maybe 2-3 decimals, and the t1 obviously is also approximate to 3 decimals, it's not the exact value. So this is what happened at two different moments in time, so negative 6.4 and 4.4. The curve, the particle was passing by this point, so we have a loop at this point. So basically loop opens at this point and then it closes at this point, and these are the values of parameter t when that happens. So okay, that's nice, which means we can set up the integral for the arc length, and I say set up because we have t1 and t2. Again, the expression of the derivative is fine, but computing the integral, that's another story. So we are here only setting up the integral thanks to the t1 and t2 that we just found and using the formula, so we cannot do much more here. And similarly, if I need to find, so this gives me the length of the arc, like the number that will come out of this. And similarly, if we need to find the area of the region enclosed inside the loop, well, we need to integrate this expression between t1 and t2. t1 and t2, we have it. The derivative is again and of x and here the y, that's quite straightforward, and we need to integrate this expression, which is not obvious immediately, so it will require some integration by parts probably. So I just here set up the integral and I leave it as is. So basically the number that comes out of this will be the area inside the loop. And here is the graphical representation of the curve that we were dealing with. So indeed we have an intersection point here, so we have a loop, so the length of the loop is given by that integral for the arc length, and the area inside was given by the formula for the area. And we found, you see, we travel along the curve, and at some moment we are here, and then some time later we come back again. So t1 and t2, those were our t1, t2, right? Minus 6.4 and 4.4. And then we had the location. So that's about it. This was just let's say a scary example when we combined everything, and you see that this can be extremely challenging because the computations can become heavy. And that's why, again, in the problems that you have to solve, you are asked for one or two properties, maybe vertical tangent and horizontal tangent, maybe just arc length, because we know that the computation will be straightforward or easy. So it will be extremely rare, or you will never face the situation where you are given a curve and asked all those 7 or 8 questions, because that would be extremely difficult. If the curve is complicated, or even here the expression is not that complicated, but computations become heavy. So I would encourage you to actually try to solve some of the questions that are suggested. You have the detailed answers also. Those are straightforward questions with quite simple computations. So please try to practice a little bit. Again, you have 2 or 3 formulas. You have formula for the slope, the second derivative, and area and arc length. So you have 4 formulas to work with. I hope you will solve some problems.